Hello. Okay, hello. I'd like to welcome everybody to our special lecture. We have a very special guest all the way from Canada. He is a writer or an author of a very famous machine learning book that I use as a textbook for my course. The lecturer today, his name is Shai Davis, and he's a professor at Waterloo University. He is, I guess, started out as a mathematician. He was supervised by a very, 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 very famous, almost fellow field medal winner, his supervisor. He got his PhD in Israel, and he spent his appointments in Cornell universities, in various universities now, and he ended up in Waterloo University and wrote this very, very famous book. I have known him for a number of years, and I have been trying to invite him, I guess, over 5 years. And I think very recently opportunity came up, and I was able to bring him here. I found out that we have many things in common. Very nice person, very compassionate person, very human-oriented person. Let me just say that I have this profile. Let's see, Shai earned his PhD in mathematics in Hebrew University. In Israel there are only 7 or 8 universities, and there are a population of 10 million. We have 50 million, and we have over about 300 universities. So Hebrew University is probably one of the best university in Israel. So that's where he got his PhD. And his son is also very smart, and he's a professor at Waterloo, and he's his colleague. Anyhow, he had many visiting faculty positions, as I mentioned, Cornell University, ANU, Australian National University, Zurich, and so forth. He's been very active in machine learning community. His citations are very, very high, and he has a wide breadth of machine learning knowledge, theory knowledge. Without further ado, let's welcome this wonderful man. And I guess we became good friends, I think, over a couple of days. And hopefully, in future, we will be able to have him here if it's possible. But let's welcome Shai Davis. Let's give him a warm applause.
Thank you very much for the nice introduction. Okay, so this is going to be a theory talk, and I don't know what is your background, so I really welcome questions. You can interrupt me anytime. If anything is unclear, if you want elaboration, feel free to interrupt and ask questions. Okay, so I'm going to talk about learning probability distributions, and this is a relatively technical talk, but it's a very important topic. So the really fundamental problem in statistical learning is that there is some unknown probability distribution or environment. Say the distribution of patients, or the distributions of ads, or whatever you're trying to understand. There is an unknown probability distribution. The environment, all you see from this distribution is subsample, and you're trying to learn what the distribution is just based on the sample that you can access. So that's a very fundamental problem. Maybe that's a description of whatever we are doing in statistical learning. And so given a sample from this distribution, we want to learn as much as possible about the distribution that generated that sample. And the first two questions to ask is, what is the prior knowledge that we have when we start this learning? And the other question is, what are we trying to learn about this distribution? So these are the two fundamental questions we have to ask ourselves. What prior knowledge are we coming into the game with, and what are we trying to figure out about the distribution? So of course, the most ambitious framework is that you assume no prior knowledge. You don't know what the distribution is like, and you're trying to learn what the distribution is. So on one hand, you don't assume anything. On the other hand, you want to learn everything. You want to know what the distribution is. So that's the kind of the most ambitious goal. You have no prior assumptions, and you're trying to find an approximation to this distribution. So we can view it in a picture like this. So you get unknown distribution D. This distribution generates a sample. Now comes the learner. The learner or the computer looks at the sample and is trying to come up with some approximation to the original distribution that generated the sample. So that's, you see, we don't assume here any prior knowledge, and we're trying to approximate the distribution to learn everything about the distribution. So what I'm claiming is that this is a very difficult challenge if we don't have any prior knowledge. So to demonstrate to you why it is so difficult, let us consider a lottery game. So assume that there is a lottery, that every week I throw 8 dice, or I randomly, every week the machine randomly picks 8 numbers, and everybody can buy a ballot, and if you predicted the 8 numbers correctly, you get a big prize. That's a lottery game, right? We all know it. And now, assume that I'm the lottery manager, and I have a nice trick how to cheat the system and become rich. So what will be my trick? I will toss the dice, say, 1,000 times. And I will record all the outcomes. So 1,000 times I will take 8 dice, throw them, record it. Throw them, record it. And now, from now on, whenever I need to run the lottery, instead of running the lottery, I will just pick from the 1,000 outcomes that I have in my pocket. You see, this is a big cheat, because now all I need is to buy 1,000 tickets, and I will mark them with all those 1,000 outcomes, and I'm guaranteed to win every single week. So it's a big cheat. But now what I ask is, how long will it take an observer to detect that I'm cheating? So just assume you are an observer, you see every week what the lottery publishes. Can you tell that I'm just picking from this small collection that I prepared? I randomly got this collection, and now I'm just picking from that collection rather than running the lottery again. How long will it take you to detect that I'm cheating? You see, this is a real problem of the type that we talked about before. There is this distribution, which is the distribution of outcomes of the dice. And there is another distribution, which is distribution of randomly picking from my 1,000 outcomes. These are very different distributions. One has a huge range, and the other one has a range of only 1,000 many outcomes. Now you get random samples. Can you tell that the random samples came from one distribution rather than the other? So you see, this is exactly the problem that we were discussing. You see a random sample, unknown distribution, you don't know anything about the distribution, and you're trying to figure out what the distribution that generated the sample. Was it a cheating distribution, or was it a real distribution? Now, if we look at this problem, you can realize that when will you catch me cheating? I think the first time there will be suspicion is the first time that the same result appears a second time. Once you see that the same lottery outcome appears a second time, you begin to worry something is wrong here. But until then, there is no way you can tell that I'm cheating, because I got those 1,000 outcomes by really running the machine. So as long as the sample size is not big enough to have repetitions, you will not be able to tell whether it came from the small distribution or whether it came from the big distribution. Which shows you how difficult is this task of learning what the distribution is from just a sample. So let me try to formalize it. So the claim is, so I'm claiming that if you don't have any prior assumption and you try to learn what the distribution is, this is provably impossible. And so the claim is that if you have sample sizes that are independent of the domain size, then you cannot distinguish between two distributions that are in total variation a half apart. So total variation is a measure of distance between distributions. I don't know how familiar you are with it. It's the maximum of all subsets of the difference between the weight of the subset in one distribution and the weight in the other. So what I'm saying is that if your sample sizes do not depend on the domain size, you will not be able to distinguish between two distributions, two candidates that generated the sample. Was it generated by candidate distribution 1? Was it generated by candidate distribution 2? Although they are very much different than each other. And the proof is that, now you see, the example that I gave you before is kind of a proof. But if you want to make a mathematical proof, so let us have a domain set of size x and of size n, and consider the uniform distribution over this n many points. And as long as we pick a sample of size less than square root of n, we are not likely to see repetitions. Right? That's the birthday paradox. I mean, the birthday paradox tells you that above square root of n you see repetitions, but we also have a lower bound, that below square root of n you are not likely to see repetitions. So we have this size capital N. As long as the sample size is less than square root of capital N, we are not likely to see the repetition. But if we don't see repetitions, it's like same likelihood that we picked from a uniform distribution over the whole domain, or maybe it was just uniform over a subset of, say, size half of the domain that contained all the points in the sample. That's exactly what happens with the cheating in the lottery. You couldn't tell if I picked from the distribution of all possible outcomes, or I just picked from the distribution of the 1,000 outcomes that you didn't know what these 1,000 outcomes were. So this is kind of a proof that as long as the sample size is not the square root of the domain size, you will not be able to tell which distribution generated your sample. You will not be able to distinguish between very different distributions. And of course, when we talk about learning, we want to get reliable answers based on sample sizes that do not depend on the domain size. Right? If I want to know about distribution of patients, I don't want that the sample will need to be proportional to the size of the population, or whatever prices, whatever the domain size is too big. So it is kind of a negative result, which tells you, you remember I said there are two questions you have to ask yourself. What are my prior assumptions, and what do I want to learn? If I make no prior assumptions and I want to learn everything, this shows you it's impossible. Okay, so that's kind of a starting point. So now, the conclusion is that without prior knowledge, asking what the distribution is, you cannot achieve it as long as the sample size don't depend on the domain size. So it really gives us two major types of questions to progress. One is assuming that distribution comes from a restricted family of distributions. Assume that I have some prior knowledge what kind of distribution it is, then I can do learning. I can get positive results. The other direction is to say that I don't assume anything about the distribution, but I don't try to learn what the distribution is. I'm trying only to learn something about the distribution. We all know that, for example, if all I want to learn is what is the mean of the distribution, then I don't need any assumptions. I'll take a big enough sample, I'll take the mean of the sample, it will be close to the mean of the distribution. So here I asked about the distribution only a limited information. What is the mean of the distribution? So I'm saying now the research splits into two directions. One direction is under what prior assumptions can you learn what the distribution is. The other direction, if you don't have any prior assumptions, what kind of information about the distribution can you reliably learn? And these are two different directions. And I'm going to show you results in both of those directions. So, and I will also discuss the question of can we characterize what learning is possible. So when we can characterize which families of distributions, which prior assumptions suffice to learn what the distribution is, and can we characterize which questions about the distribution can I figure out without assumptions. So in both cases I want to have complete understanding of when is this task possible. Okay? Any questions at this point? So now I'm going to get into a little bit more concrete results. I will show you results in each of these two domains. So we start with learning distributions with prior knowledge, and we have these nice results of learning mixture of Gaussians. So that's a very common problem. I mean, one of the common assumptions about distributions that you see about the environment is that it is a mixture of Gaussians. Say if I want to look at the distribution of patients, maybe there is a Gaussian of patients around young Caucasian female, and there's a Gaussian of distribution of patients around old black men, and there are different kind of Gaussians, and the population is a mixture of those Gaussians. So that's a very common assumption, that we approximate a population or environment by a mixture of Gaussians, and the question is, so I make this assumption. The underlying unknown distribution is a mixture of Gaussians. Can I learn it? And we show that this is possible. And then, of course, we will ask the question of can we characterize which families of distributions are learnable. There is another technical point here that I will not discuss, but I would then go to trying to ask what properties of distributions, what properties of the prior knowledge suffice in order to enable learning. Okay. So I want to cover several results. So the result of learning mixture of Gaussians, then results on characterizing which families of distributions are learnable, under what assumptions can you learn, and then show that realizable. I will not get into it because I don't have time, but also I'll discuss what kind of properties can you learn about distributions without prior assumptions. So we have results in all of those areas, and in all of those areas these are results from the past 5 years. Okay, so let me start with what are the tools of trade that we have for machine learning. So if you're taking any course in theory of machine learning, there are these tools of trade. There is pack learnability, there is learnability by empirical risk minimization, there is weak learning. If you remember, weak learning is instead of trying to find out your target with arbitrary good approximation, you just ask, can I learn my target up to approximation, a third? That's weak learning. There is uniform convergence. There is existence of sample compression schemes. There is a finiteness of combinatorial dimension. So these are all tools that we use traditionally in learning. And the nice thing is that if you do binary classification, if your task is just to predict a binary label, then all of those are equivalent. If you try to do binary classification, you know that it's learnable only if it is learnable by empirical risk minimization, if and only if you have a finite VC dimension. Each of those tools give you equivalent result. But that's kind of a lucky situation when you are trying to predict binary classification. It is not the case when you're trying to learn what a distribution is. Remember that when we are trying to learn what a distribution is, we don't have supervised data. It's unsupervised learning. You just get a sample with no labels. So if the sample is with labels and you have just two labels, all of those conditions are equivalent. But once we go to different domains like many labels or unsupervised learning, then some of those tools hold, but some don't. Equivalence breaks down. So one tool that I'm going to use in some of my results is the tool of sample compression schemes. So I don't know if you covered it in the courses that you take, but it turns out that the existence of sample compression schemes is equivalent to learnability. That's not a very popular tool, but it's very useful for the theory. So I will describe now what are those sample compression schemes. Okay, so sample compression schemes are basically a manifestation of the Occam razor. The Occam razor, probably you heard about it, that you have a collection of different explanations. You should always prefer the simplest explanation. And a manifestation of this is the idea of sample compression schemes. So what is sample compression scheme? So you can think of it as a game. So we have a class of models, say the class of all Gaussian distributions. This is our assumption, and the learner knows what this class is. And now we are playing a game. There is a game between Alice and Bob. There is a distribution that generates the data, which is D. It is coming from the family F. And Alice knows it, but Bob doesn't know what D is. And then Alice draws a sample from this distribution. And Bob only knows what is the family, he doesn't know what D is. And now she is passing on to Bob only a few points from this sample. So the question is, can Bob recover all the information that was in the sample from just a few points? That is called sample compression scheme. Rather than sending all of the sample, you send only a few points. So just to be concrete, think, for example, that assume that we are doing a binary classification and the target is a rectangle. Everything inside the rectangle is plus, everything outside the rectangle is minus. And Alice gets a sample, and the sample is labeled plus for all the points in the rectangle and minus all the points outside the rectangle. So she can send to Bob only 4 points, the top point, which is plus, the lowest plus, the leftmost plus, the rightmost plus. By these 4 points, Bob could draw a rectangle that contains all of the positive points, and he knows he can label all the points in the sample of Alice. You didn't need all the points. You only needed those boundary points. Or if you're learning a linear classifier, these are the support vectors. You don't need all the sample, you just need few points which are close to the boundary. So that's a compression scheme. We take a sample, we can send to Bob only a small subset, and it suffices for learning. So Lielstone and Varmut defined sample compression schemes for binary classification, and they showed that if you have sample compression scheme, then the class is learnable. So the class of rectangles is learnable because we have a compression scheme. The class of half spaces is learnable because we have easy compression. And after 30 years, Shai and Emir Yodayov could show that this is also a necessary condition. That is, every learnable class has a sample compression scheme. If your class is, but that's for binary labeled learning. For the very simple task of just learning binary classification. Okay, so for binary learning classification, path learnability is equivalent to the existence of a compression scheme. And then when we want to talk about distribution, this becomes more difficult, but we still can show one direction. And this is kind of a very general phenomenon. If this is the paper on learning mixture of Gaussians, and we use this idea of sample compression. And we say that if Alice can pass to Bob only t many points, then you can learn with sample size that is just t over epsilon squared. So if Bob wants to approximate the distribution up to epsilon, the sample size that he needs is only so much, where t is how many points do you need to compress the sample. So one direction of this equivalence goes on, extends to learning probability distributions, and we used it to learn, to show, solve the problem of learning mixture of Gaussians. So let me show you now what compression do we need for mixture of Gaussians. So just to recap where we are. We are trying to show that we can learn probability distributions under the assumption that they are mixture of Gaussians. We have this tool of sample compression. We know that if we have a sample compression, then we get learnability. And we get a bound. So how do we do sample compression for Gaussians? So assume that, let's start with the simple case. The simple case is that my Gaussian is over the one dimension, and it's only one Gaussian. Eventually I will want to talk about Gaussians in high dimension and mixtures of many Gaussians. But let's start with the simple case. Why is it running ahead? I don't know. Okay, so we have this distribution, and Alice draws a sample from this distribution. So Alice draws this sample. Now what can we pass to Bob such that Bob will be able to figure out what the distribution is, roughly? So the point is that if the sample is big enough, you're going to have 2 points such that the average of these 2 points is close to the mean of the distribution, and the distance between these 2 points is close to the variance of a distribution. So I can compress a Gaussian in one dimension to 2 points. If Alice saw a large enough sample, all she needs to do is pick 2 points because she knows what the distribution is, and pass them to Bob, and Bob will say, oh, the mean of the Gaussian is the mean of the Gaussian is the average of these 2 points, and the variance of this Gaussian is the half the difference of these 2 points, and he knows what the Gaussian is. So we showed that very simply one-dimensional single Gaussian is compressed. Now what do we do if we have a mixture of Gaussians in one dimension? So the nice thing about compression is it is very modular. So now assume that I have a mixture of Gaussians. And Alice now gets a sample from this mixture of Gaussians. But now it is very easy to get a compression, because what she will do is she will pick 2 points for each of the components. Alice knows what is the mixture. So if you have a big enough sample, you can pick 2 points from each of the components. So we see that if you have a mixture of k Gaussians in dimension 1, Alice just needs to pass to Bob 2k points, and he can recover everything. And so it extends. The nice thing about this tool of compression is that it is modular. If I do it for one distribution, I can do it for a mixture. What about going from one dimension to high dimension? So we can also do this. I don't have it on the slide. I don't know why. But we can also show that if you have a Gaussian in dimension d, you can compress it to d square points. For every component, for every projection, you will get 2 points on this projection, and you look at all the combinations of 2 dimensions and all the components in the covariance matrix. For each component of the covariance matrix, you will only need 2 points. So the conclusion is that if I have a mixture of k Gaussians in dimension d, then I can compress to size k times d squared. D squared is to compress a Gaussian in dimension d, because I need 2 points for every component of the covariant matrix. And k is multiplied by the number of components. So I get that I can compress to k d squared, and by our previous results that if you have a compression to size d, then you can learn with as many samples as just t over epsilon squared, we get this bound for how many points you need to learn, how many sample points you need to learn mixture of Gaussians in high dimension. And we could also show that this is tight, that you cannot do, this is complete answer to the question of learning mixture of Gaussians in high dimension. So yeah, this improves previous bound, it is a tight bound, and the compression idea can be extended even beyond the assumption that the distribution is a mixture of Gaussians to agnostic setting. The agnostic setting is saying, I just want to find the mixture that approximates my distribution best. So I'm just trying to approximate my distribution with the mixture of Gaussians. Okay, so, yes?
Two questions. So passing Bob the only 2 points, and Bob, you mentioned that Bob should be able to reconstruct the corresponding distribution. So is it equivalent to saying that finding minimum number of sample sufficient for reconstructing sufficient statistics?
No. There is a subtle point here.
Okay.
The subtle point is that when Bob sees the sample, he doesn't have Alice to help him. Alice knows how to pick 2 good points, 2 points which are most informative. But Bob doesn't know which 2 points. There is no Alice. But Bob can simulate Alice. Bob can say, if there was an Alice, she would give me 2 points. So let me try all possible pairs of points. And then I will get a finite set of candidates. For every 2 points that Alice could have sent me, I will get a candidate distribution. And now I just have to decide between a finite set of candidates. And we know how to do it. You see, we reduce the problem of learning a mixture of Gaussians, which is infinitely many candidates, there are infinitely many Gaussians, to a problem of just learning if you have size m sample, you have m square pairs, you will just have m square candidates, and you have to pick between them. Okay? Yeah. So there is no Alice, but Bob, knowing that there is a compression scheme, he can simulate Alice and handle all the possible outcomes, all the possible messages that he could have got from Alice. Yes?
Another question. If you had a distribution that is defined by 2 statistics, and it seems like you're encoding the 2 statistics by the sample points. One is the average, one is the difference between them. Can this be generalized to any distribution defined by 2?
Right, almost. The only component which is missing is that you have to make sure that if you see enough points, you can find 2 points that represent your statistics.
Okay, so if you want to use this theory in real life, let's say you have an Alice that knows the distribution by taking lots and lots of samples, because I mean we never know what the distribution is of any data, so we take a lot of samples, we approximate it very well, and then we pick those samples so that small number of samples so that the distribution can be defined.
Right.
So Alice is someone who had a lot of data and would have a good approximation of that, and in order to save computational time for various other downstream tasks, you just pick a small subsamples, and that would be it.
But two points here. First of all, as I said, Alice doesn't exist. We have to simulate this Alice.
Mm-hmm.
So the initial sample size matters, because if I want to ask how many candidate pairs could have Alice sent me, it's m squared, where m is the size of the sample that you needed in the beginning.
Mm-hmm.
So we also depend on the size of sample you need to guarantee that they are good representatives. Okay? But it definitely can be extended to many other situations. Yeah. Okay, so what do we know now? We know that the open problems that are left is, first of all, can we do it efficiently? Can we do it in computation, which is polynomial, say, in the dimension and the number of Gaussians? And can we characterize which families? You see, we saw now two examples. We saw that mixture of Gaussians we can learn, but then we saw that if I just tell you it's a uniform distribution over some subset, you cannot learn it because of the lottery. So can we distinguish between these two situations? Can we characterize which properties suffice for learning and which properties will not suffice? That's a very natural question that arises. So the focus of what I'm going to talk about now is how do we characterize learnability. And again, I mean, if you look at classical machine learning, we know that if you want to characterize binary classification, there is the visit dimension. If you want to characterize online classification, online learning, there is the Littlestone dimension. It's less famous, but it's a very nice dimension. If you want to characterize weak learning, learning of real-valued functions, we have a paper from, I think, 96 or 97 that comes up with a fat shattering dimension. So for many learning problems, we have a dimension such that you look at the class, you figure out what the dimension is, and based on it, you know whether the class is learnable or not. Right? Now the question is, can we do something similar when we want to learn distributions? You see, it doesn't appear here. So there are some problems that for which we did not come up with a dimension. So learning a probability distribution is one of them, or classification, binary classification. But you know that when we talk about VC dimension, you probably notice that this is the worst case. VC dimension is finite, characterizes learning distribution free. But assume that you know something about distribution. Can you get a better characterization of learning based on your knowledge of a restricted family of distributions? And learning real-valued functions. So these are cases of problems for which we did not have a characterization. And what we showed in this, in a recent work with my student Tosca Lefner, is for all of those problems, there exists no dimension. Which is, if I have time, I will explain what do I mean by there exists no dimension. How do we phrase it? We have to define what the dimension is if I want to see that there exists no dimension. So, okay. So let me go into this and show you how do we show that there exists no dimension. So we need a definition of what do we mean by a dimension that characterizes learning. And there are two notions, two roles that the dimension plays. So now I kind of rely on assuming that you know what the visit dimension is. So the visit dimension plays two roles. One of them is a quantitative role. If you know the visit dimension, you know upper and lower bound on the sample complexity. You know that if you want to learn up to precision epsilon with probability 1 minus delta, you need d over epsilon examples. So the visit dimension gives you a quantity, tells you how many samples you're going to need for any precision. That's a quantitative. But it also gives you a qualitative notion, because we know that the class is learnable if and only if the visit dimension is finite. So it plays two roles. It tells you what's learnable and what's not, but it also tells you how many samples you will need for a learnable class to succeed. So we want to define these two abstract notions of dimensions that generalize each of those properties. So the simplest one is, you see, we want to have a notion of a dimension so that the class will be learnable if and only if this dimension is less than infinity. And we also want the quantitative one, is that you will have this notion of a dimension of a class. And if you don't want to know how many samples you need, all you need to know is what is the dimension of the class. There is something here very subtle that you have to realize. When we talk about VC dimension, you can have the class of half spaces, you can have the class of Gaussians, you can have the class of decision trees, you can have the class of linear half spaces, you can have the class of rectangles, of balls, whatever. You don't care what the class is. All you care about is the VC dimension, and now you know how many samples you need. All you ask about the class is the VC dimension and what are the precision and confidence parameters. So the dimension kind of extracts all the relevant information from the class, and that's all you need to know. So that's our notion of a quantitative dimension. And for qualitative dimension, you want just that it will be a function that maps the classes to numbers, and if the function is finite, it's learnable. If the function is infinite, it's not learnable. So we generalize those notions. That's what I was just explaining, that all the information that you need to know what is the sample size needed to achieve precision epsilon is encompassed into this dimension. And we show that under this definition, there can be no dimension for learnability of distributions. And similarly, for the more complex definition is the qualitative definition. What does it mean that the class is learnable? So we have a set of properties like you shatter a set of size D, you shatter a set of size D plus 1, if you shatter sets of arbitrary sizes, you're not learnable. If it stops at some point, you're learnable. So we also generalize this property, and all the previous kind of dimensions that I talk about, they all satisfy our general definition of a dimension, and we can show that this is a result that's under submission now, that no such dimension can exist for each of the problems that I mentioned that we don't have a dimension yet. So the proof idea I will do if I have time. I'm kind of running short, but I will be happy to, either if I have time I'll explain it here, if not I'll be happy to explain it to any of you that wants to talk to me.
So,
I have more results that I want to show.
Okay, so
It's not the end, but yeah, about what you want to ask.
I just wanted to say, I mean, VC dimension is based on the complexity of the hypothesis.
Right.
Right, and as you mentioned, it's binary. Now, if we talk about, we're trying to learn the distribution.
Right.
Okay, so maybe that could be cast as a regression type of problem, which requires maybe infinite complexity, VC dimension of infinity. So in that case...
No, so let me give you a few examples. So one example, there were attempts, and we're not the first one to try to address this problem. So one famous attempt it was saying, if you have a collection of distributions, you want to know if it's learnable or not. So for any pair of distributions, you can look at the set of all points on which distribution 1 gives more weight than distribution 2. So you see, for every pair of distributions in your family, you get a subset. The subset of all points that look heavier under distribution P than under distribution Q. So for every pair you get a subset, and now you get, for the collection of distributions, you get a collection of subsets. And the question, if this collection of subsets has a finite VC dimension, is the collection of distributions learnable? And it turns out that in this direction it is correct. If this collection of subsets had a finite VC dimension, the family of distributions is learnable. But the other direction was open. Is it the case that whenever a set of distributions is learnable, these subsets have finite VC dimension? That was open. Or, for example, when we talk about learning real-valued functions, when learning regression functions. So we introduced this notion of fat shattering dimension, which is kind of imitating the VC dimension. So you can ask, is fat shattering a necessary sufficient condition for learning? So those are all kind of dimensions that are in the same flavor, and we can show that no such dimension can solve the problem of learning distributions.
Just one more quick question. So VC dimension is binary for binary classification.
It's for binary classification, right?
We have Rademacher, which is for multi-class
Right.
white. So why wasn't Rademacher considered in any of your?
Because Rademacher is not a property of the class. It's a joint property of the class and the marginal. I'm asking what properties of the class alone can characterize learnability. The Rademacher complexity involves the marginal. It tells you now I can learn with respect to this marginal. Then you use the VC dimension to show that if the VC dimension is finite, no matter what the distribution, the Rademacher will be finite. Okay? Okay, so here we got a negative result. Let me try to just quickly mention, you see, I talked about two directions of research. One of them was what prior assumptions suffice for learning. The other direction was if you don't have prior assumptions, what properties of distributions can you recover? So let me say something about this other direction. So, learning to answer queries. You have a set of queries about the distribution that you want to answer, and you don't know anything about distribution. You want to know which queries will I be able to answer, without any assumptions about what the distribution is coming from. So more generally, you can say you have a sample and you have a set of queries, and you want to know, if I want to know, can I approximate every query over the sample, then this is called uniform convergence. I will not get into it, that's something we understand very well. If you have a collection of queries and you want to be able to approximate all of them, that's uniform convergence. We know how to characterize it. But in many cases, we have a different problem. And the problem is, you have a collection of real-valued queries. You have a collection of queries, and you have an input sample from an unknown distribution, and all you want to get is, give me some query that gets the maximum value. So I'm saying this is a very, even more practical problem than estimating all the queries. So for example, a query could be, I have a distribution of students that apply to the university, and I don't want to estimate what is the proportion of students from Korea that apply, what is the proportion of students from India that apply, what is the proportion of females that apply. What I want to know is just which group of students is most likely to apply. So rather than trying to estimate all of the queries, I'm just asking, give me the subset that is most likely to occur. Okay? So you see just a finite sample. There is a collection of possible queries. You just want to give me one that has the maximum likelihood of being hit, or the highest value. If you view them as random variables, you have a collection of random variables. Which of them will get the highest value under your unknown distribution? So many problems can be phrased in this way. In binary classification, you can ask which hypothesis will make the minimal error. Making the minimal error is like having the maximum score. Or you can ask in multi-class classification, which function into multi-class will have the minimal error. Or you can ask, say you want to do k-means. So you have an unknown distribution, you want to find k-centers. I'm sure you know the k-means problem. You have an unknown distribution, you want to find k-centers that will minimize the distance to the centers, right? So I don't need to estimate the cost of every possible set of centers. I just want to find one set of centers that gives me the minimal cost. So if my set of queries, what will be the cost of every collection of centers? I don't want to answer all of them. I just want to give me one set of centers that minimizes the cost. So I'm saying this problem of expectation maximization, we call it, is a very relevant problem. We know very well how to answer the problem of estimate all of them. Estimate all of them, it's just a finite piece dimension. But I want less than that. I just want to find one which maximizes my profit or minimizes my cost. Okay, so I'm just showing that many problems can be cast in this way. And actually, this phrasing of the learning problem goes back to Vapnik. Vapnik, you know, was one of the founders of modern statistical learning, and he already said this is what he called it, the general learning problem. The general learning problem, you have a set of queries or a set of random variables, unknown distribution, you get a sample, give me the random variable that gets the maximum value or the minimum value. So Vapnik already asked this question. He didn't know how to characterize this. He knew how to characterize the uniform convergence with the Vapnik-Jablonskis dimension, but he couldn't answer this question. So, I can tell you the end of the story. So with a set of very smart colleagues, we showed that this problem cannot be answered in a set theory. So we involved logic, and we saw that the answer to this question is independent of mathematical logic. But let's postpone it and let me show you a little bit what is the game here. So you have a collection of, here is the game. You have a collection of domain subsets. Say all the students that came from China, all the students that came from Korea, these are subsets of my domain of students. And you get a sample, and you want to say, find a set in the collection whose weight is close to the maximum under the unknown distribution. I don't know what the distribution is. Students, tell me by looking at the sample reliably which country sends me most students. Okay, so if the class is the class of all subsets, then we can already see that the characterization that we had before doesn't hold. Because if I have the class of all functions, and you cannot answer what is the estimate of every possible function. Because if my domain is infinite, it has infinite with dimension, we cannot answer it. But if I have the class of all subsets, so, okay, now I'm trying to, if you lost me, I'm trying to connect to you again with a simple problem. You have some domain set X, an unknown distribution, and you see a sample, and I ask you which subset of X, among all subsets of X, has the highest probability of being hit. What is it? What's the answer? You have a domain set X, say the natural numbers. Unknown distribution over the natural numbers. Give me a subset of the natural numbers that has the largest probability of being hit. What is it? Yes? What? No, the largest probability, a subset. I want a subset. What will be the subset that has probability 1 of being hit? The whole set, the whole domain. So I can very easily answer what is the maximum likelihood subset in this case, although I cannot estimate all of them. So what I'm saying, this problem is easier than uniform convergence. It's easier than estimating every subset. I cannot estimate every subset, but in this case, I can very easily tell you which subset is the most likely. That's just because I had in my collection the whole collection. Okay, so we know that it's a different problem. So we call it Emacs learnability, and we try to characterize it. So which classes of subsets are Emacs learnable? For which classes of the domain, which class of subsets will you be able to tell me which is the most likely one? So let me, I want to deviate from the slides because I'm running out of time. How much time do I have? Okay. So, because we use here, again, a notion of compression, but the notion of compression is a bit complex, so I will not get into it, but I want to give you another example. Okay, so consider the following example. So to be concrete, let us consider that I have an X which is an infinite domain, and my H is all finite subsets. And now I'm trying to do, our claim is that compression will give you learnability, and we are trying to do compression. So we have here a game between Bob and Alice. So here is the game. Alice gets a finite set, a finite sample, as before. She needs to pick a subset S prime and send it to Bob. And Bob will need to give me back a finite set that includes all the points that Alice had. So this is my new compression scheme, and I can show that this is equivalent to learning. But look at this for a second. What is the game? So assume that we are over the natural numbers. Alice gets a subset of the natural numbers. And now she wants to set only few points to Bob, and Bob needs to recover a subset of the natural numbers which is finite and includes everything that Alice had. Can they do it? Again, we have the natural numbers. Alice gets some points. She wants to send to Bob, say, only 1 point, such that Bob will be able to recover a finite set that includes everything that Alice saw. Alice doesn't tell him what samples did she get. She only gives him 1 point. But he should be able to give, what will she send him? The maximum point, right? If we are over the natural numbers, Alice got a finite set. There is a maximum point. She will send to Bob the maximum point. Bob will say, take all the points below it. It's a superset of what she had, and it's finite. So we can do it, if the domain is the natural numbers. But now what if the domain is the real numbers? Can we play the same game? So now Alice gets a finite set of real numbers. She wants to send to Bob just a few points that he will be able to get a finite set that covers everything that Alice said. But now it's the real numbers. If we are in the real numbers and Alice got these points and she will send the maximum point, and Bob will say, oh, all of the points below it, what's wrong with it?
You get infinite number.
It's an infinite number of points. Bob has to recover a finite number of points. So the game becomes very difficult over the real numbers. And we showed, we showed that...
We have 30 more minutes.
What?
You have 30 more minutes.
30 more minutes? Oh. The question is probably not my time, but your attention span. Right. So this is the game between Bob and Alice, and is there a strategy by which for every subset Bob can get a small subset and get a superset of S, and okay, so it turns out that it really depends on the size of the domain. We know that if the domain is countable. If the domain is finite, it's trivial, because if the domain is finite, what can Bob do? Send the whole domain. It's finite. If the domain is countable, we just saw it. Bob gets the maximum point in the natural numbers. But what if X is uncountable? So we showed that if it is uncountable, Alice can set k points if and only if the cardinality is less than Aleph k. So now we need set theory. So that was very lucky for me because I did my PhD in set theory, so that's my mother tongue. So what are the Aleph k's? So let me just slightly give you a divergence on this. So we know that there is the first infinite cardinal is countable. And Cantor's theorem tells us that the real numbers are uncountable. So the real numbers are bigger than countable. But the question is there anything in between? Is the size of the real numbers the first size that is not countable? or other sizes in between. And this is called the continuum hypothesis. And in 1960, mathematician Paul Cohen proved that this is independent of set theory, which means we will never be able to answer this question. So you see, the question is, we have the natural numbers, we have the real numbers, we know the real numbers are bigger, but is this the first bigger cardinal? So the first bigger cardinal, we call it Aleph 1. The second bigger cardinal, we call it Aleph 2. And Aleph K is the case in the hierarchy of cardinals. And then we can talk about Aleph Omega, which is the limit of all those Aleph Ks. And then comes Aleph Omega plus 1. And we can keep going and going and going. And the question is, where in this hierarchy? So you have countable, Aleph 1, Aleph 2, Aleph 3, and so on. And you have the real numbers. And you ask, how big is the real numbers? And all we know is that it's not countable. But any more refined answer is independent of set theory, which means with the tools of mathematics, we'll never be able to find the answer. Now we show that we will have a compression if and only if, say we are playing it over the reals, if and only if the reals are less than the case infinite number. But this is something we don't know, we can never know. So we showed that you will never be able to know if Alice has a strategy in this game or not. Because the answer depends on the size of the real numbers. And we don't know what is the size of the real numbers. So you see, we took the problem of learning the maximum likelihood set, which is an important statistical problem. We turned it into a compression game between Bob and Alice. Then we showed that this compression game between Bob and Alice is equivalent to an old question in set theory, the continuum hypothesis, which does not have a solution. Therefore, there is no solution to when the compression game has an answer. Therefore, there is no solution to which sets of queries can you answer. So if we were looking for a dimension, you remember I went into two directions. I said, what assumptions about the distributions will suffice to learning everything? Or, if you don't assume anything, which set of queries can you answer? Right? Now the queries that I was restricting my attention to, the queries were very simple. Give me a subset that has highest probability. This question translates into this compression game, translates into continuum hypothesis. So we can show that there can be no mathematical answer to this question. So that was a very big surprise of a connection between machine learning, very basic problem in machine learning that Vapnik already defined as the basic general statistical learning, and a big open problem, classical set theory, the continuum hypothesis.
So we cannot learn the distribution.
What?
So we cannot learn the distribution.
It's not about learning, it's about the second direction. The question is, which queries can you answer? So here we focused on the queries. You have a collection of subsets. Which of them has the highest weight? And when can you answer it? And the answer to the when can you answer it is that we will not be able to give you an answer. Right. So, okay, so that's basic about infinities, Paul Cohen's result, the rating, that he showed that it's independent of set theory, and then our conclusion is that equivalent to monotone compression. If we look here, you see, of all those tools, so if we look about learning this type of answering queries, bulk learnability is equivalent to weak learnability, is equivalent to compression, but it's not equivalent to all the others. And the compression became equivalent to the continuum hypothesis, and therefore we cannot answer all of those questions. So let me skip a bit and go to the conclusions. So there can be no combinatorial dimension that characterizes this type of maximum likelihood learning. Okay, I don't want to get into the set theory too much. Okay, so what can this independence tell us? Where is it coming from? You see, we ask a very basic questions. We ask, when will a finite sample suffice to approximate the best subset up to a third? There is no infinite number here. We want a finite sample, you want to approximate up to a third. How come it suddenly became independent? So thinking about it, we found a big hole in the theory of machine learning. And the hole in the theory of machine learning is that when you look at PAC learnability, we define learning by functions. You ask, is there a function that takes samples and gives you a hypothesis? But in reality, we don't just want any function, we want a learning algorithm. You see, so the VC dimension theory tells you when is there a learning function. But in reality, we don't care about arbitrary functions. We want an algorithm that learns. If we reduce the function to the question, to asking when is there a program that can learn, which is the most natural question. And then suddenly the VC theory collapses. So we could show that if these are finite, programs are finite objects, there is no independence of set theory, but the VC theory dies. So we showed that we defined the learnability requiring computability. We require that the learner will be computable, will be a program. And we ask, do the Vapnik-Chervonenkis results survive? And we show that they break down. We can show that there is a class of VC dimension 1 that you cannot learn it with a program. You see, you remember the classic beautiful VC dimension theory told us a class is learnable if it has a finite VC dimension. But Vapnik defined learnable as a statistician. He's not a computer scientist. He defined learnable by there is a function that takes samples and gives you a hypothesis. We are computer scientists. We don't want just a function. We want a program. If we want a program, Vapnik's result collapses. We can show that there is a class of VC dimension 1. Of course it's learnable, but no program can learn it. So we are in this kind of interesting connection. If we talk about learning functions, we get into independent of set theory, which is a complete puzzle. We don't want to get there. But we can tell ourselves we don't care about learning functions. We learn about learning with programs. If we want to learn with programs, we have to go and revisit the basic theory of machine learning because the beautiful VC characterization no longer applies. So there are more recent results that I got with a group of my students, and it's still an area of a very recent area of lively research. What can you characterize learnability with programs rather than learnability with arbitrary functions? Okay, so we also got a different result on this, and not being able to characterize. Okay, so I will stop here and I will take questions because I threw at you a lot of results and a lot of techniques, and I'm sure it's confusing. So I'll be very happy to clarify any point that you are curious about.
I have one question that I think, actually two questions. So you were going to talk about whether distribution is learnable, right?
A set of distributions isn't learnable. Right.
So, and you had two settings. One setting was assuming that that distribution was part of some class of functions.
Right.
Maybe a parametric form.
Right.
Parametric form, and you gave us maybe what is it?
I gave one positive result, on mixture of Gaussians, and I gave a negative result that says you will not be able to find the characterization of this.
Okay, so you had, you said that you were going to state two results. One was whether if you had assumed some prior,
Right.
prior, and in that case you could do it, and you could sort of Alice could sort of encode the information into the samples.
Right, that was the
Then
positive result, right.
That was the. Now you didn't also in that part. If it's a Gaussian mixture, it's not only the mean and variance, but you also have the weight of the
Right.
Gaussians,
Right.
which you did not mention.
I did not
mention.
mention. Right, good
So-
point. You caught me on a good point. The Alice can also send an approximation of the weights, and it still will consist the compression. So we allow in the compression. Let me repeat Chang's question. It's a very good question, because when I talk about mixture of Gaussians, it's not just a question which are the covariant matrices of different Gaussians, but also there's a question, what is the weight of each of the Gaussians in the mixture? But it turns out that the set of weights can be compactly compressed, always. You just need some discretization of the weights, and depending on your target epsilon,
Quantizing, is it?
quantizing the weights. Quantizing the weight depending on epsilon, and so Alice also sends to Bob the set of weights. And when we argue that Bob can imagine and simulate all the answers from Alice, it includes that Alice also sent him a discretization of the weights.
Okay.
So the paradigm goes through.
Okay, so with regards to that, with regards to the machine learning problem that a lot of people here are studying, they have samples. So are they Bob or are they? Can there be Alice?
No,
Or
we are all
so
Bob. We are all Bob because Alice is all-knowing. You know, we are in the female empowerment. The women are all-knowing. Alice, Bob is a male. He doesn't know much. He needs Alice to help. Now there is no Alice. Bob is a lonely bachelor, so he fantasizes Alice, and he fantasizes all the possible answers that Alice could give him. The point is that this set of answers is finite. Once he sees a sample, it's just a finite set. And if you have a finite set of candidates, deciding between them is relatively easy.
Okay, so that was your conclusion. So it was good news when you had a prior or a parametric form that you assumed. You
That I could compress.
Right, that you can compress. That was a good one. The second one, without any prior, there's no hope. There's no hope, right?
No, there's no hope. I was saying that there are several results. One of them said, if there's no prior and you want to learn what the distribution is, there's no hope. That's the lottery option.
Okay.
But now we were talking about characterizing. I asked, what set of queries can you answer? You want to answer which subset of the students is most likely. And if you want to characterize this type of learning, we will not have a characterization. We will not be able to find a characterization.
So from both of 1 and 2, I mean, machine learning is probably 80 or 90% will be to characterize the distribution of the data. If you have the data distribution, then you can probably solve most of the machine learning problems that we have, right? So you're saying your message, your final message will be to have a good prior. Then you would be able to
if you have a good prior, but I cannot tell you in advance which priors will be good enough. That's the problem. I mean, if you give me some prior knowledge, we can try to investigate it. But there's no such thing like you give me your prior knowledge, I will extract a dimension and tell you this prior knowledge is sufficient or not sufficient.
Right.
I will not be able to do that.
So you have a good educated prior guess. If it's good, then you can do it.
Right.
If you do, if you have a bad prior, then you will fail.
Right, but I cannot tell you.
You're right, of course.
That's the problem. Are there any other questions? Yes.
great lecture. My name is Wang Jin. I have a question for the 1,000 lottery example.
Right.
I understood that with the 1,000 pre-picked lottery, we cannot know whether it is from the pre-picked or the picked from the original distribution.
Right.
Then I have a question. If we train machine learning with model with n samples with the empirical loss minimizing,
Right.
then the model can optimally.
No. Which when you say empirically ERM, right?
Yeah.
The question is ERM over what set of hypotheses? If my set is, I mean, you want to train the, I mean, there is the set of all possible outcomes of the lottery.
Yeah.
Right? For ERM, you want to say, here is a collection of subsets. Which of those collections generated the data? But if the collection is all the subsets, because you don't know what came in the 1,000, then the VC dimension of this will be the size of the domain. And the number of examples that you will need will be like the size of the domain.
In most cases, which is infinite.
In many cases, it's infinite, but
You have
even when you
infinite number of
discretize.
data, that's what you're
Right,
saying.
right, right. You see, because potentially you don't, if you knew in advance that those 1,000 points came from one of a few subsets, then you can do ERM of these few subsets. But you have no clue. Those 1,000 points could have come anywhere. So you have to take into consideration all possible subsets. So also possible subsets of a set X as this dimension the size of X. You will need too many examples for that.
Thank you. So if we have an ERM model with n samples, but we don't know
The class over which you're doing ERM. Right.
so which distribution?
No, it's not which distribution. It's what does it mean to do ERM? You have a class and you want which member, for each member of my class, estimated error. And then give me the one that has minimal error. But it's among all the members of my class. If my class is too big, the ERM will require too many samples. If I don't have any constraint on the subset, then ERM is overfitting. Yes.
Yeah, my name is Yosan Shin. Thank you for the great talk. I have two questions. You mentioned that for the Gaussian mixture approximation, if you assume that you know the parameter, then you can approximate the weight too. But the weight is the subset of the real number, and therefore the
Right.
yeah, so therefore.
So no. So I mean, you have k distributions. You have a weight for each of them. But if you just want to learn to approximation epsilon, you can allow yourself small mistakes in the weights. So you discretize the weights according to your epsilon, and you get just a finite set.
The second question is for the distribution you have no idea, then this is you can't really have the subset which provides the maximum.
Right, that's the answer I was just giving him, yes.
But are there any characteristics you can actually have?
That's exactly what we showed, that I cannot characterize which subsets, I can characterize which subsets you will be able to do ERM over. But if you just want to find the one that's most likely, you can do better than ERM. And for that, we cannot have a characterization. Okay.
Okay, I guess that's end of our talk. Let's give a big hand for our speaker.